Welcome to today's deep dive. It is fantastic to have you joining us.
Yeah, really glad you're here with us.
We are looking at a stack of documentation and platform specifications today that essentially serve as a blueprint for how the physical world of tomorrow is going to be built.
It really is. It's an incredibly dense set of specs.
Right. Specifically, we are examining the architecture of a platform called MatXra,
MatXra.
developed by Exabyte Inc. and their Japanese counterpart, MatXra Japan KK. And they refer to this platform as the Materials R&D Cloud.
Which is a bold claim, but as we'll see, it's pretty accurate.
Our mission for this deep dive is to understand how this ecosystem is taking material science out of these isolated local hardware setups and dragging it into a highly collaborative, high-performance cloud environment that's powered by AI.
It is a massive structural shift for the field. I mean, if you think about the history of material science, it has traditionally been defined by very slow physical trial and error.
Like Thomas Edison in his workshop kind of trial and error.
Exactly. Edison famously tested thousands of different materials. I mean, from bamboo to platinum, just to find the right filament for the incandescent light bulb.
Wow. Bamboo.
Yeah, bamboo. It was an incredibly tedious empirical process. And even as we moved into the modern era of computing, that physical bottleneck was largely just replaced by a computational bottleneck.
Right. Waiting for computers instead of waiting for chemicals to react.
Precisely.
Okay, let's unpack this, because that computational bottleneck is exactly what MatXra is targeting. The documentation leans heavily into this term in silico prototyping.
Right.
Now, for anyone following the space, we know that means bypassing the physical beaker entirely and testing these compounds via computer simulation.
Right, doing it in silicon on a chip.
Exactly. But what does the day-to-day reality of that actually look like for a researcher using this platform compared to, the old way of doing things?
Well, the old way usually involved a highly fragmented workflow. A material scientist would have to secure time on a university supercomputer.
Which I imagine is highly competitive.
Oh, incredibly. Or they'd use a massive on-premise server cluster if their company could afford it. They'd use a clunky command line interface to submit a job. And then they would wait hours, sometimes days, in a queue.
Just waiting.
Just waiting. And then they'd receive this massive text file of raw data. And if they made a single syntax error in their initial setup,
Oh, no.
yeah, they'd have to start all over, get back in the queue.
That sounds agonizing.
It really was. So what MatXra provides is an in-browser integrated environment. They have taken that entire fragmented, frustrating process and centralized it.
Okay.
From a standard web browser, a researcher can design atomic structures visually. They can run those highly complex physical simulations through high-performance cloud computing, and then immediately use that data to build machine learning models.
All from Chrome or Safari, whatever.
Exactly. Anywhere in the world.
The scale of what they're achieving with this centralized approach is what really jumps out from the platform metrics. I mean, according to the specs, they aren't just running a few isolated experiments to prove this works.
No, not at all.
They have documented 36,889 simulation workflows.
Yep.
And they have 64,078 distinct materials stored in the system.
It's massive.
They have run over 73,000 calculations, 72,462 to be exact. But the number that truly shifts the paradigm, for me at least, is their predictive output.
Yes, the properties.
Right. They have successfully predicted 251,084 material properties.
What's fascinating here is the philosophical implication of that final number.
How so?
Well, predicting over 250,000 properties means we are moving way beyond simply testing materials we already know about.
Okay.
We are effectively creating a vast, searchable periodic table of synthetic possibilities.
Wow, a searchable periodic table.
Exactly. It's not just data hoarding. It's organizing the data so that it becomes instantly actionable. In the traditional model, if a researcher spent 6 months running complex calculations on a specific alloy,
Right.
that data often just lived and died on their local hard drive.
Just stuck on a laptop somewhere.
Yeah. If a colleague halfway across the world needed that exact same data 5 years later, they would likely have to run the simulation completely from scratch.
Because they wouldn't even know it existed.
Right. MatXra creates a globally accessible memory bank.
Which is an organizational nightmare that I think you, listening right now, can probably relate to, regardless of your field.
Oh, absolutely.
Just think about trying to track down a crucial piece of information buried in an old email thread or trying to find a specific file on a highly disorganized shared drive,
It's the worst.
it paralyzes momentum entirely, and the MatXra documentation describes their interface as purpose-built and highly customizable.
Which is key.
Right, which essentially gives scientists a perfectly organized digital workspace.
Mm.
It allows them to focus purely on the chemistry and the physics rather than the IT logistics of file management.
And removing that IT burden is absolutely critical because the actual science requires immense computational weight.
Because they're doing this at the atomic level.
Exactly. We're talking about simulating the interactions of atoms and electrons. That requires incredibly dense mathematics. And to do that, the platform relies on legacy physics engines that have been the gold standard in the scientific community for decades.
The documentation specifically names engines like Quantum Espresso,
Yep, a classic.
VASP, LAM-MPS, and GROMASS. I look at these engines kind of like highly specialized power tools in a master wood shop.
That's a good way to look at it.
You know, you have your table saw, your router, your drill press. Each one is designed for a very specific heavy-duty task.
Right.
Historically, you had to build a massive physical workshop just to house them, and you needed specialized knowledge to maintain and configure each individual machine.
And the power to run them.
Exactly. What MatXra has done is take all these distinct simulation engines and made them available on demand in a unified cloud-based workshop.
If we connect this to the bigger picture, hosting those legacy engines in the cloud is really only step one. The true innovation of MatXra is acting as a bridge. It connects those rigorous, established rules of traditional physics directly with modern data analytics and AI infrastructure.
So merging the old and the new.
Exactly. You are taking engines like VASP, which strictly calculate quantum mechanical realities, and feeding their output into machine learning models that can predict how a material will behave at scale.
And doing it fast.
In a fraction of the time, yes.
That sounds great in theory, but when you say they are integrating legacy physics engines with modern AI, my immediate thought goes straight to data translation.
The formatting.
Yeah. VASP and GROMASS were not originally designed to speak the same language as a modern neural network.
Definitely not.
The raw output from a quantum mechanics simulation usually requires heavy manual formatting before it's digestible for an AI model. How is MatXra actually bridging that gap without losing data integrity or requiring scientists to spend weeks just writing custom translation scripts?
That is the exact friction point they are solving, and they're doing it through strict interoperability.
Interoperability.
Right. The source material highlights their use of open-source data standards to organize materials information alongside a web-based designer for interoperable modeling workflows.
Okay, break that down for us.
By enforcing a universal open-source standard across the entire platform, they ensure that the output from something like Quantum Espresso is automatically formatted in a way that a machine learning algorithm can instantly read.
Oh, so it's baked into the system.
Exactly. They have built an automated pipeline. The very moment a physics simulation finishes, that data seamlessly flows into the AI predictive model without a human ever needing to manually parse a text file.
Here's where it gets really interesting. Let's look at how that automated pipeline translates into tangible, real-world breakthroughs.
Let's do it.
The documentation provides a series of case studies that move us from just platform architecture to actual applied science.
Right, rubber meeting the road.
Exactly. The first one involves a team of researchers led by Professor Dario Roca at the University de Lorraine. They utilized the platform for surface catalysis, specifically to compute adsorption enthalpies in zeolites with high accuracy.
To give that some necessary context, zeolites are highly porous minerals,
Porous like a sponge.
very much like a sponge at the molecular level. They are the absolute workhorses of the petrochemical and manufacturing industries. They're used for everything from refining oil to carbon capture and water purification.
Okay.
The key to their utility is how well different molecules actually stick to their surface.
Stick to the sponge.
Right. And adsorption enthalpies is simply the scientific term for measuring the exact amount of heat energy released when a gas or liquid binds to that solid surface.
And getting that measurement right is incredibly difficult without physical testing, right?
Historically, yes, it was very difficult. It requires pinpoint accuracy at the atomic level. But if you can compute those adsorption enthalpies with high accuracy in a cloud environment,
You can skip the physical lab.
exactly, you can design vastly more efficient chemical filters or catalysts without having to physically synthesize hundreds of variations in a wet lab.
That is wild.
You basically let the cloud do the heavy lifting of figuring out which molecular structure will trap carbon dioxide most efficiently, for example.
That makes perfect sense. And the second case study jumps into an entirely different sector, which is energy storage.
Very hot topic.
Very. We have researchers led by Professor Nicole Adelstein at San Francisco State University. Her team used MatXra to investigate the electronic properties of next-generation materials for solid-state lithium-ion batteries.
Solid-state batteries are essentially the holy grail of modern energy research right now.
Because of the safety issues with current ones.
Partially, yes.
Yeah.
The lithium-ion batteries in your phone or your electric vehicle right now use a liquid electrolyte, which is exactly why they can occasionally overheat or even catch fire.
Right.
Solid-state batteries replace that liquid with a rigid, solid structure that promises vastly higher energy density and unparalleled safety.
But there's a catch.
There's a massive friction point. Finding a solid material that allows lithium ions to flow through it just as easily as they flow through a liquid.
Which means analyzing thousands of potential crystal lattice structures to see which one provides the path of least resistance for those ions.
Exactly.
And simulating that ion flow at the atomic level requires exactly the kind of high-performance computing that MatXra is offering. If Professor Adelstein's team had to rely purely on local hardware, rendering those atomic structures would take an absolute eternity.
Precisely. It would slow down the innovation cycle to a crawl. And that same hardware bottleneck applies to the third case study mentioned in the specs.
The advanced alloys.
Right. A team from Intermolecular Inc. used the platform to study equilibrium geometries and formation energies for advanced lightweight alloys.
Let's define those terms for clarity. Finding equilibrium geometries means using the software to calculate the lowest energy, most stable physical arrangement of atoms in a newly proposed alloy.
Right, the most stable shape it can take.
And formation energies refers to calculating exactly how much energy it will require to actually manufacture that compound from its base element.
Exactly. If you are trying to design a new lightweight alloy to make commercial airplanes more fuel efficient, you need to know both of those metrics before you even attempt to cast the metal.
Before you spend millions on a prototype.
Right. And the unifying thread across the zeolites, the solid-state batteries, and the lightweight alloys is that the math required to simulate them is exceptionally heavy.
Heavy lifting for the processors.
The cloud HPC infrastructure of MatXra entirely removes the limitation of local hardware. It allows these distinct teams to run massive calculations simultaneously.
So what does this all mean? When we step back and look at the human impact, the way this alters the daily ecosystem of R&D, it is a story of democratization.
It really is.
The platform user testimonials are very telling in this regard. Dr. Kazuki Mori from ITOCHU Techno Solutions highlighted that the accessible interface drastically accelerates the process of training new users in nanoscale simulations.
Think about the traditional learning curve here. Training a graduate student to properly configure VASP via a command line interface.
Just typing code?
Yeah, ensuring they understand all the distinct flags and variables. That could take months before they run a single useful experiment.
Wow.
But by wrapping those dense physics engines in a modern, visual, web-based workflow, you aren't dumbing down the science at all.
Right, the math is the same.
Exactly. You are simply removing the software engineering barrier to entry. Dr. Jun Koyanagi from the Tokyo University of Science echoed this perfectly in his testimonial.
What did he say?
He noted that MatXra provides top-tier computational resources in a highly cost-efficient manner, which significantly reduces the friction of educating new group members. It allows scientists to focus on being scientists rather than acting as system administrators.
And then we have the impact on the corporate side as well. Dr. Sergey Barabash from Intermolecular, which is a company that was subsequently acquired by Merck, pointed out that leveraging state-of-the-art simulations in the cloud significantly accelerated their overall R&D timeline.
Which is huge for a company like Merck.
Right. But when we talk about corporate R&D, especially at that scale, my immediate concern is intellectual property.
Oh, absolutely. The security.
If all these groundbreaking, highly proprietary formulas are being developed in a shared cloud ecosystem, how does MatXra ensure that a commercial entity's multi-million-dollar battery design doesn't accidentally bleed over into a university's open research project?
Security has to be foundational in a system like this, not an afterthought. And the MatXra documentation explicitly outlines their protocols for this.
Okay, how do they handle it?
Well, they utilize advanced encryption for all data, both when it is at rest on their servers and when it is actively in transfer. But more importantly, they employ strict network partitioning.
What does that mean in practice?
It essentially creates impermeable digital silos within the cloud. It ensures that one account's computational space is entirely isolated from another's. There's no crossover.
Okay, that makes sense. And it's worth noting that while they have optimized for ease of use with the web browser interface, they haven't locked out the power users who still want granular control over their work.
No, not at all.
The platform maintains remote access tools like command line interfaces, remote desktop capabilities, and RESTful API access.
The API is a big deal.
Yeah, so if a massive pharmaceutical company already has their own internal automated data pipelines, they can use the API to plug MatXra's cloud computing power directly into their existing infrastructure.
Which brings us to perhaps the most disruptive aspect of the platform.
The business model.
Exactly. Historically, getting this level of high-performance computing access required multi-million-dollar institutional grants to purchase physical server racks and expensive software licenses.
Just massive capital upfront.
Massive. It inherently restricted cutting-edge material science to just a handful of elite universities and giant corporations.
That's why their pricing strategy is so compelling. They haven't just built a better tool, they've totally restructured who gets to actually use it.
Right.
They offer a completely free tier, fully capitalized in the docs, with a one project limit.
A free tier for this level of computing is wild.
It is. That allows an independent researcher or a curious student to test drive the actual full power simulation tools without spending a single dime.
And then it scales from there.
Right. From there, it scales up to a PRO tier for $100 a year, which offers high-severity support, and an enterprise tier for $1,000 a year. That handles team collaboration, up to 5 members, multiple projects, and urgent support.
Right.
What is remarkable to me is not the specific dollar amounts, but the strategy itself. They have essentially priced enterprise-grade R&D software like standard SaaS subscriptions.
This raises an important question.
What's up?
How does the fundamental nature of global innovation change when the tools of discovery evolve this radically? We're talking about a true paradigm shift here.
Tough.
For the last 50 years, the capacity to simulate complex atomic structures was literally locked behind physical doors. Now, anyone with an internet connection and a solid understanding of chemistry can access those exact same resources via a standard web browser.
It completely flattens the playing field.
Entirely. The next major breakthrough in carbon capture technology or biodegradable plastics, it might not come from a billion-dollar laboratory anymore. It could just as easily come from a small, dedicated team leveraging cloud HPC from their laptops.
It fundamentally changes the geography of innovation.
It really does.
So, to quickly recap our journey today, we have explored how MatXra is taking the most rigorous, complex, legacy physics tools in the world.
Engines like VASP and quantum espresso.
Right, and integrating them into a secure, highly accessible cloud interface. By pairing those heavy-duty engines with open-source data standards and advanced AI, they are not only solving the computational bottlenecks of material science.
No, they're going way beyond that.
They're opening the doors for unprecedented global scientific collaboration.
And as we consider the trajectory of this ecosystem, I really want to leave you with a final thought to mull over.
Lay it on us.
We have established that MatXra has already cataloged over 64,000 materials and predicted over 251,000 properties. It houses a vast, interconnected machine learning infrastructure.
Right.
Now, right now, scientists are primarily using this system to simulate and optimize materials that they have personally hypothesized.
Materials they thought of first.
Exactly. But what happens when this interoperable system crosses a threshold and stops merely simulating known or guessed materials?
Oh, wow.
Right. With that much interconnected data and processing power, we're rapidly approaching a horizon where the AI begins independently generating the blueprints for highly optimized, entirely theoretical compounds.
Just inventing them from scratch.
Yes. It will start designing materials with physical properties that humanity has never even conceived of before, and simply handing us the blueprints to build them.
That is an incredible horizon to look toward. A future where our cloud computing environments become the primary inventors of our physical world.
It's coming faster than we think.
Well, thank you so much for joining us on this deep dive. We hope it gave you some profound new insights into the materials R&D cloud and the future of science. Keep exploring, keep asking questions, and above all, stay curious. We will catch you on the next deep dive.